Okay, I have managed to rectify the mistake. It's not a very big one, and I confused myself with the numbers. So we have seen the calculation till this stage, right? After this 2, for some reason I brought in 35, and that created all the confusion. So let us carefully see what we can do instead of bringing 35, what we can do after this stage. So here what we do, all the things that you see here are present here. We are writing this term extra, a1 a2 x square plus a1 a2. This we can do because this is a multiple of the polynomial x square plus 1, and it will get engulfed in this ideal. Okay, so that's why we can write this extra term. Now after this, what happens? Here we have a1 a2 x square plus the rest of the terms containing x plus this 2a1 a2 and that extra a1 a2, they give us 3a1 a2, and the other terms 5a1 b2 plus 5a2 b1 plus b1 plus b1 b2, they remain like they are. Okay, plus x square plus 1. Now the first part is this a1 a2 x square plus this terms containing x, 10a1 a2 plus a1 b2 plus a2 b1 times x, plus now in place of 3 we can write 25, because 25 minus 3 is 22, which is divisible by 11. In other words, 25 is congruent to 3 mod 11. So that's why modulo 11, they are the same congruence class. So here we have 25 a1 a2, and the rest of the things are same. 5 a1 b2 plus 5 a2 b1 plus b1 b2 plus the ideal. Now this whole thing, this whole coset can be written as the product of these two cosets. You see carefully, if you multiply these two cosets, then what will you have? You have to multiply these two polynomials now, this one and this one. What will you get? a1 a2 x square, we have that here, 5a1 b2, no wait, what I am trying to say is this, 5a1 a2 x plus 5a1 a2 x, that gives us 10a1 a2 x. Then a1 b2 x plus b1 a2 x. Okay, so that gives us this x terms. Then 5a1 times 5a2 gives us 25a1 a2 plus 5a1 b2 plus 5a2 b1 plus finally b1 b2. And according to the definition of our function, this equals the f image of this coset, and this equals the f image of this coset. In place of a2x plus b2, you will have a2x plus 5a2 plus b2. So we finally see that our f really respects also multiplication. That means it's a ring homomorphism. Okay. Thus, f respects multiplication too, and hence is a ring homomorphism. Okay. F is also easily seen to be one-to-one, that is injective. Why? because we have proved that it's a ring homomorphism. Then for injectivity you have to just show that the kernel of F consists of only the 0 element. Now the kernel of F will be any element in the kernel of F. If this is an element in the kernel of F, say, then it will be mapped onto the 0 element of the range field. And what is the map? Ax plus 5a plus b plus x square plus 1. This is the image of that element. If it becomes equal to the 0 element, then that means this polynomial, because it is either 0 or it has degree less than 2. So for this to happen, this polynomial must be equal to 0. That means a must be equal to 0 and 5a plus b, these two coefficients must be equal to 0. But if a is 0, then 5a plus b equal to 0 implies b is also 0. So this element, this element means that element, ax plus b plus x square plus x plus 4, that element in the kernel is the 0 element. Okay, 0 element means just the ideal x square plus x plus 4, and that's why, because of that, F is 1 to 1. It's a straightforward argument, a straightforward calculation. And finally now we have to show that F is onto also, because then only we can claim that the two fields are isomorphic. And for that we have this. Moreover, for any element, that mistake could have been easily avoided had I not brought that 35 unnecessarily. Anyway, now everything is good again. For any element, cx plus d plus x square plus 1. Now any element in the range, in the second field, you have to find an input for which this is the output. We have, for this element, the proposed input is this, cx plus d plus 6c plus x square plus x plus 4 belonging to fx divided by x square plus x plus 4, such that if we calculate the f image of this element, cx plus d plus 6c plus x square plus x plus 4, what do we get? According to the definition of our function, it will be cx plus 5c plus that is 5a plus b, and the b is d plus 6c plus x square plus 1. So this is equal to cx plus d plus 5 plus 6 is 11, and since the modulus we have in the field is 11, so this term vanishes, it is 0. So we have cx plus d plus x square plus 1. So we get the original element back. So this acts as a pre-image of this element, as an inverse image. Thus, F is onto. This shows that F is a bijective homomorphism between the two fields, and hence the two fields are isomorphic. Hence, we conclude that the fields fx divided by x square plus 1 and fx by x square plus x plus 4 are isomorphic. And here the solution ends. I am not going to make it any longer. We will see the other exercises in the next video. This is, you can consider this as a small part attached to the previous video where we failed to complete this problem. Okay, so see you in the next video.